Good morning, welcome to a new video for physics. Today we are going to talk about electricity, and more specifically we are going to study the physics of series circuit. So a series circuit is essentially a circuit for pretty much all we care about, where the electricity will only have one path to go through. The electrons will only have one path. Okay, so we have already studied the symbols for schematics. So let me show you a little schematic right here to illustrate what a series circuit would look like. Okay, so let's have a little battery right here. Okay, so one cell battery. We would have the positive side right here. We would have the negative side right here. And we're just going to have two resistors. Let's call this resistor 1. Let's call this resistor 2. And those two resistors together will constitute a little circuit. Okay, a series circuit. Very simple one, but nonetheless circuit. When you do simulation on software, sometimes you need to put a ground right here to show that the negative terminal of the battery will be considered to be 0 volt. But really what we want is the difference of potential between the two terminals of the power supply or the battery. Okay, so here I'm just going to write E for the battery. That's my electromotorist force. Remember we talked about it. That's the force that is going to allow the electrons to leave their atom and just go through the circuit. Okay, so let's say that this one is going to be a 5 volt power supply. Okay, so the convention for flow of electricity is that it's going to go from the plus toward the minus. We know it's not true, but it doesn't matter that much, because for all calculations related to this class and frankly others, that's going to work. It's just a convention. Okay, so this is the current, and since the electrons only have one path to go through, we know that the current through the first resistor, which traditionally we write I1, will be equal to the current going through the second resistor. Okay, both resistors are going to act as loads for the source, that is the battery. And we're going to represent the voltage drop by each one of them by a little arrow like this going against the current. Okay, this one we're going to label as VR1. This one we're going to label as VR2. So in Tinkercad, we did a few labs where we used the multimeters to measure all of this. And you realize that when we measured things, you realize that E was equal to VR1 plus VR2. Another way of writing that down will be to say that the sum of the source voltage is equal to the sum of the load voltage. So all the resistors, light bulbs, speakers, all of this is the load. It's what uses the electricity. And the batteries, the power supply, those are the sources. Okay, so we can generalize this little formula right here by saying that the sum of the voltage of the sources is equal to the sum of the voltage of the loads. Okay, now this here is an important statement in here. But if I were to say that in a loop this is true, then I would have essentially stated Kirchhoff's voltage law. Okay, so in a loop, in any given loop, I should say maybe, we can say that the sum of the voltage of the sources is equal to the sum of the voltage of the loads. What is a loop? Well, a loop is essentially part of the circuit where the electricity does not have the option of leaving that part of the circuit. Okay, so if I, for example, show this here, you see that when the electricity goes like this, it comes back to the battery right here. This here is a loop. Okay, so series circuit will only have one loop like this. We're going to go back to that concept of loop when we study parallel circuits, and I will illustrate. So it's going to be a little clearer then. Okay. And what is the current? Well, the current will be the same everywhere here. All right. So when we have a circuit like this, what do we do to essentially measure everything? Because what we did in the past is we went on Tinkercad, we built little circuits, we took the multimeters, we measured everything. But the goal here for us is to predict what all those voltages dropped are and what the current is everywhere. Okay? That's the goal. Okay? So the goal is to predict, and we're going to do that by calculating, but predict the current at any place in the circuit. And this goal, by the way, is not just a goal for series circuits, it's a goal for any kind of electrical circuit. It's to predict the current at any place in the circuit and to predict the voltage dropped by any of the components in the circuit. So here are the components, any of the loads, right? The components here are the two resistors. And I drew resistors, but they can represent other things, like it could be a light bulb, it can be a speakerphone, it can be something, a photoresistor or whatever. Doesn't matter. Now, the idea, and this strategy that I'm about to share with you is something that you have to do regardless of the type of circuit, right? It could be series, could be parallel, could be hybrid, it could be delta Y. We're not going to go in there in this class, but it can be anything. Okay? So the idea is this. Number one, you're going to calculate the equivalent resistance. That's going to be the first thing. Okay. Number two, you're going to calculate the current out of the battery. Okay. Once you have this, you're going to be able to calculate the voltages dropped by the components. And I will show you how to do that, don't worry. By the components and the current through them, through the components. Okay, so at our level, all we'll deal with is resistance, which are linear in nature. Okay, we are not going to do any calculations at this level of physics involving coils, solenoids, capacitors, this kind of things. Okay, this requires different kind of mathematics. Okay, so how do we do that here? Well, since today we are focusing on series circuit, I'm going to tell you that in series, the equivalent resistance, which is what we need to do for the first part right here, In series, the equivalent resistance is equal to the sum of the individual resistances. Okay, so if you look at our diagram above, essentially it's going to be just R1 plus R2. It's very, very simple. Okay, for series, it's not the same formula for other things. Okay, so this will be for part 1. For part 2, calculate the current out of the battery. Well, for this, we need to use something called Ohm's Law. Okay, so Ohm's Law is probably the most important electrical law when we do circuit analysis. Okay, there are others, but this is the first one and it's very fundamental. So Ohm's law is essentially a law that connects 3 of the things we have measured so far in our electrical circuits. So it will connect the voltage, it will connect the current, and it will connect the resistance together. Okay. And essentially, Ohm's law says that the voltage will be equal to the current times your resistance. Now, you need to be careful. In order to for this to work, the voltage has to be expressed in volts, the current has to be expressed in amperes, and the resistance has to be expressed in ohms. Okay. The SI unit that is used to talk about electricity is the ampere. Okay, so you need to make sure that you use this like that. Now, let me show you a little something to remember Ohm's law. I'm going to make a little circle right here. I'm going to split it in half. And that looks like a Pokemon ball right there. And I'm going to write V R I. Okay, so voltage V, resistance R, current I. And if you want to, for example, calculate the voltage in a circuit, put your finger over the V right here. So imagine we don't see the V anymore. And so if you want to calculate the voltage, what do you see? You see R times I. So that will give you the first formula. V equal R times I. If you want to calculate the resistance in the problem, put your finger over the R, pretend this R is not here anymore, and so you're going to have V over I. So if you want R, it's just V over I. Of course, we can do all of this algebraically, but this is a nice little device right here that I wanted to share with you. And if you want to know the current, put your finger over the I, pretend we don't see the I anymore, and so you're going to have V over R. So this here is going to be what we need for Ohm's law. Okay, we have this formula, and this formula right here. And this is Ohm's law. And that's what we need to use for part 2 and part 3. Okay, so let's go back to the problem right here. So we see that, we see Kirchhoff's voltage law, we see what we need to do. So let's have an example with numbers to illustrate all of this. Okay, let me redraw my circuit over here. Let's have an example. Okay, so let's have a little battery. We are going to make it a 5-volt battery like before. This is going to be my plus side, my minus side. Let's make it a simple little problem for now. Okay, we're going to make more difficult problems later, but for now let's just have R1 equal 100 ohms. Let's have R2 equal 400 ohms. And the current goes back like this. Okay, so what are we looking for? As usual, we're looking for the current right here. Let's label as I. The voltage drop by this one, we're going to call it VR1. The voltage drop by this one, let's call it VR2. So the first thing we're going to do, again, is we're going to calculate the equivalent resistance. According to the formula, it's going to be equal to R1 plus R2, which is going to be equal to 100 ohms plus 400 ohms. It's equal to 500 ohms. Okay? So literally we are done right here. The equivalent resistance is 500 ohms. All right, done. Part 2, we're going to measure, or not measure, we don't have a multimeter. This is a theoretical exercise here. We are going to calculate, I should say, the current leaving the battery. Okay, so if we want to have the current, what we're going to do here is we're going to look at Ohm's law, and we want the current. The current is I, so we're going to use this formula right here. We're going to use V over R. Okay, let's do that. I is going to be equal to the voltage. In this case, since we're talking about the current out of the battery, we're going to have the voltage which is going to be E, over the resistance, which is the resistance of the circuit, so the equivalent resistance. So it's going to be 5 divided by 500. Okay, so 5 divided by 500 is going to be 0.01 amp. It's a little weird to write 0.01 amp. I prefer to write 10 milliamp. Okay, so the current leaving the battery is 10 milliamps, and this current is the current that's going to go through the first resistor and the second resistor. Remember, in a series circuit, the resistance is the current. Sorry about that. The current is the same everywhere in series. Okay, so now we're going to calculate VR1, and we're going to calculate VR2. So we are calculating a voltage, and like I told you earlier, we're going to use Ohm's law again. So if I go back up here, what Ohm's law do I use if I want the voltage? This one. The voltage is a resistance times the current. Okay, so this is going to be the resistance R1 times the current I. This will be the resistance R2 times the current I. Okay, therefore it's going to be R1. R1 is 100 ohms times, I need to have it in amps, so I need to write it like this. That's going to give me 1 volt. VR1 is equal to 1 volt, and VR2 is going to be 400 ohms times 0.01 amps equal 4 volts. VR2 equal 4 volts. Okay. Okay. All right, so quick little example right here. Very good. Very straightforward, and it's typical of the kind of things that you will have to do as well. Okay. So often in class, when we talk about things, you guys ask, okay, fine, but okay, that's physics, that's part of what we're supposed to learn, but what do we really do with that? How can this be used, So the issue with very simple little examples like this is that there are not that many applications, but remember that this will be a part of a bigger circuit in the vast majority of the time. There is, however, a very, 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 very important and common application of simple circuit like this. And I'm going to give you an application example right here. And this application example is called the voltage divider. Yeah. So before I show you the work involving the voltage divider, I want to tell you what a voltage divider does and why it's important to know about it. Okay, so let's imagine that I'm going to build a circuit that controls a 12-volt motor. Okay, so in order to control my 12-volt motor, I need a 12-volt battery. I'm drawing a single cell battery right here, but it doesn't matter. Okay, let's imagine we have a 12-volt battery right here. That's our positive side, our negative side. Okay, and this is going to be powering the motor. But we want some, pretend you want some electronics that's going to be used to decide when the motor is going to be on, at what speed the motor is going to be on, if it's going to go in one direction, if it's going to go in the other direction. So there are a bunch of electronics like this. But the issue is this. Most of the electronics that you can use, it's going to be TTL, so transistor logic, or CMOS. They use different voltage levels than 12 volts. If you put 12 volts into CMOS integrated circuit, it's going to destroy it if you put it in a TTL circuit also. But so basically that 12 volt is what we need for the motor, but we might not only need 12 volts. So one option would be to use other power supply, maybe at 5 volts, at 3 volts, but it might be cumbersome. So using one battery and one battery only might be a good thing. So what I'm going to do here is I'm going to take the battery and I'm going to use the 12 volt for the motor, but I'm going to send that power right here, that 12 volt. I'm going to send it to a voltage divider to make it into a 5 volt and a 12 volt. So I will still have the 12 volt available, but also will have a 5 volt to power my electronics. Okay, so that's the idea of a voltage divider. How do we do it? It's very simple. You're just going to do it with two resistors in series like that. Okay. So between this point and this point right here, we're still going to have our 12 volt, right? We're still going to have our 12 volt right here. But what we would like here is to determine the values of R1 and R2 such that, for example, we have 5 volt right here between this point right here and this point. That means that if I were to take a multimeter and measure the voltage drop just by R2, that will be 5 volt. Okay, that will be 5 volt. And if we go back to the previous problem, if I put a multimeter over this one, I'm just going to see 1 volt. If I put a multimeter over this one, I will just see 4 volt, right? So this first example, I gave you the resistances and I said, all right, what is the voltage drop with this battery by those resistors under those conditions? Here, it's almost like the opposite problem. Here, the question is, we have a battery. I'm not giving you R1 and R2. This is what I'm asking you to do. Find what R1 and what R2 should be such that I have 5 volt dropped by R2. By the way, if I have 5 volt dropped by R2, in other words, if VR2 is equal to 5 volt, what would automatically be the value of VR1? You can pause the video if you want a little bit of time to think about it. But remember what we wrote above, right? We wrote above, we have Kirchhoff's voltage law, that E was equal to VR1 plus VR2. So 12 is equal to 5 plus VR1. Therefore, VR1 will be equal to 7 volts. Okay? So, how do I do that? Well, we're just going to trust the guidelines that I gave you above. We are going to first calculate the equivalent resistance. So the equivalent resistance is going to be equal to R1 plus R2. But I don't know R1 and I don't know R2. It's okay. You do what you can within the guidelines. You trust that I have your best interest at heart and I'm trying to teach you how to do those things. So that's all we can do. That's all we can do. We'll move on now. Part 2, what is the current? Well, the current, according to Ohm's law, is going to be equal to the voltage of the battery, E, divided by the equivalent resistance. So it's going to be E over R1 plus R2. Okay. What do we do then? Well, we're going to calculate VR1 and VR2. But we're going to concentrate on VR2 since VR2 is what we want, the 5 volts. So I'm going to say that VR2 is equal to R2 times I. Again, this is Ohm's law, which is R2 times E over R1 plus R2. Okay, so let's rewrite it as VR2 equal R2 over R1 plus R2 times E. And I'm going to highlight or box this answer for now. And then I'm going to do a little bit of algebraic manipulation such that we can figure out what R2 and R1 might be to reach our goal of VR2. Okay, so we know that VR2 has to be 5 volts and E has to be 12 volts, right? We know that. But let's just leave it like this for now. Let's replace at the end. So if I divide both sides by E and I take the reciprocal of everything. So let's first divide both sides by E. Then let's take the reciprocal of everything. We're going to have R1 plus R2 over R2 equal E over VR2, right? Now, R1 plus R2 over R2 is the same as R1 over R2 plus R2 over R2. Therefore, R1 over R2 plus 1 is equal to E over VR2. Therefore, R1 over R2 is going to be equal to E over VR2 minus 1, but 1 we're going to write it as VR2 over VR2. And so we can say that the ratio of R1 over R2 is going to be equal to E minus VR2 over VR2. And this is what we're going to be using, this formula, in order to determine the resistance in circuits, in voltage divider circuits. So for us, we know that E is 12 volt, VR2 is 5 volt, so we need a ratio of 7 over 5. Okay, so that means that if R1, for example, is 7 ohms and R2 is 5 ohms, that will meet our demand for the voltage. But there is a problem if you use 7 ohms and 5 ohms. Those resistances are so small, then your current is going to be super high, and then essentially you're going to melt, literally melt the wires of your circuit. So you want to keep that ratio of 7 over 5, but you don't want to have values that are too small. So I'm just going to make it 7 kilo ohms right here and 5 kilo ohms. 700 would work, 500 would work. 70 and 50 might still work, but yeah. We're getting into other considerations if we want to really determine all of this, like current, like battery longevity and things like that. Okay, which is not really important for this example. Okay, so this is my lesson on series. Make it yours, and thank you for paying attention. Take care.